Yep.
Okay, it's working.
Okay, cool. So Peter Wills gave a very nice talk on this issue of how did life begin. And of course, in order to have life, we have to have quite a complex biochemistry going, but then somehow it has to be encoded by genes so that it can continue. It also has to be encased in some sort of a membrane, something that will disperse away. And so there's a number of issues, and the problem is very far from solved despite a number of promising developments. There's been many models and ideas put forward as to how life began. There's some very specific scenarios, like the ideas of Mike Russell and Bill Martin, that life began in hydrothermal phase. They sketched a very detailed proposal for how that could have occurred. It's in the second role, but it's a step in the right direction. Indeed, life may well
Maybe that can show.
Oh, yeah, okay.
Clip it somewhere.
Indeed, life may well have begun in hydrothermal vents, as I'll explain later. And there's these other ideas, such as Ganti's kinetron, Robert Rosen's metabolism replacement systems, which are going to somewhat closely related in some ways to some ideas I'm going to discuss shortly. So when you look inside metabolism of even very primitive organisms like E. coli, it's vastly complicated. And in there you see many features like cycles, things like the reverse citric acid cycle, for instance, which has been proposed as a candidate for early life. And the idea of cycles in networks is one that's also attracted the attention of mathematicians. This was an early paper by the famous combinatorialist Bolobas and Rasmussen, where they looked at this question of, if you have a random graph, you have vertices, you put arcs uniformly at random. At some point, you're going to get cycles forming. And so you want to ask questions like, how many arcs do you need to add to first get a cycle? And when those cycles first appear, will they be small cycles? Will they be big? As many of you will know, when you start adding arcs to a set of vertices at random, a transition occurs. To a certain point, the directed graph is all somewhat highly disconnected. Once a certain threshold is passed, you get a giant, strongly connected component, which will have many, many cycles in it. Strongly connected means for any two vertices, there's a path in the component from the first to the second, and also from the second back to the first. So I got interested in this after reading this book, as I'm sure many of you may have come across this idea of Stuart Kauffman, that the formation of a set of polymers that are involved in reactions and which catalyze each other's formations could lead to, at some point, a autocatalytic system. So the reactions here in mind were just very simple ones. You take two polymers, we've just got two bases here, but you could have four or any number, and you stick them together. That is a ligation, or you can cut them. That's the opposite reaction, that's called cleavage. And so he imagined a system like this, where you had some food source, you had these monomers, just single amino acids or whatever, and you have these solid arrows. They correspond to one or two of these reactants going into a reaction and a product coming out. But you also notice you have these dotted arrows. They correspond to catalysis, meaning that this peptide here, or polymer, catalyzes that reaction. So the black dots here refer to reactions. Why is catalysis important? Because all biochemistry needs it. Every reaction inside any metabolic system, inside a cell of any sort, is catalyzed. It has to proceed quickly and in a synchronized way. Catalysis is essential to life. And although most catalysts are quite complex now, they're enzymes and so on, they hide often within them things like metals, like iron, which were probably the original or close to the original catalysts in early life. So the idea that Kauffman had was if each molecule has a certain probability P of catalyzing any given reaction, As your polymers get longer and longer and the system gets larger and larger, at some point you're going to have some system that's sort of self-sustaining and every reaction is catalyzed. Well, it's a nice idea, but as Senora Lipson pointed out, it requires a huge amount of catalysis to take place. If you have polymers up to a certain length n, even just with 2 letters, the number of them is in the order of 2 to the n. The number of reactions, though, is in the order of n times 2 to the n plus 1. So if each molecule has a fixed probability of catalyzing any given reactions, then the expected number of reactions that each molecule will catalyze is going to be P times the number of reactions. In other words, it's going to grow exponentially with the polymer length, with n, the length of the longest polymer. And that's true, but the question is, well, what happens if each molecule just catalyzes 1 or 2 reactions? And maybe we don't, I mean, in Kaufman's model, the whole system became one big autocatalytic network, but maybe we don't need that. You know, when life started, maybe there was just a little subsystem of that inside this big system that was autocatalytic. All we care about is there was one somewhere. It may have only been 1% of the whole system. So what do we need? I haven't said what an autocatalytic system is. We need to be able to build it up from basic food set, and you want to make sure all the reactions are catalyzed. Now, to a mathematician, that's incredibly sloppy. Doesn't precisely say what it is. So let me do that. I have to do this, unfortunately. This is a bit boring. But first of all, we need to say what a catalytic reaction system is. You've got a set of molecule types, X, a set of reactions, R, a pattern of catalysis, C, and a food set. Okay, and a catalysis function just is a function that assigns to each molecule a set of reactions that catalyzes. So here's an example of a catalytic reaction system. We have a food set, just one molecule F. The circular molecules, these circles here denote the molecule types. The squares denote the reactions. The solid arrows denote reactants going into a reaction and products coming out. And once again, the dashed lines represent catalysis. Okay, so this is a catalytic reaction system. Okay, so is that clear so far? You can think of it either in that graphical way or more formally as described above. Now, what are we looking for? Kaufman never really formalized this, but this is how I'm going to formalize it here. We're looking for what's called a reflexively autocatalytic and F-generated set. So it's a subset of the reactions. It has to be non-empty. It has these 2 properties. First of all, each reaction is catalyzed by a product of at least one reaction in that subsystem, or perhaps by an element of the food set. That's the reflexively autocatalytic property. The second is we can order these reactions. They could have taken place in some order, the first reaction, then the second, then the third, so that each reactant of a given reaction is a product of an earlier reaction in the system, or it's in the food set. That's the food generated condition. Okay. And that's the notion of what we call a RAF, R-A-F, very unfortunate choice. It sounds like the Royal Air Force. I've given this talk in the UK and they say, why'd you call it RAF? Well, anyway, so here's an example of a catalytic reaction system. And this subset here corresponds to a RAF. So we'd have these 2 molecules forming this. This would be the first reaction. This reaction out here, even though it's catalyzed and even though it's got a food element there, that's not part of the RAF. It fails those conditions. You can check that if you like. So, important point. If you think of, a lot of people think of catalysis as, you know, well, if I've got this reaction A plus B gives C and it's catalyzed by X, I may as well just write that as A plus B plus X gives C plus X. It sort of goes in, it comes out, it's not used up. Problem is that, so, you know, if we took that view, we'd really just need this second, we could just focus on that second condition, the F generator. Why bother about the catalysis? Yes?
just to understand, why do you need each reaction to be catalyzed by a product of the system?
Yep, that's just what we want.
Okay, and then you exclude the possibility that there may be a feed-in loop that feeds into the system, but does not require their product.
Yeah. Mhm.
Okay.
So the reason we don't want to think this way about catalysis is very simply that if a catalyst isn't present, if the catalyst, say X, was not present, then this reaction couldn't occur. On the other hand, if a catalyst for the reaction A plus B gives C isn't present, that reaction can still happen, it just happens more slowly. Okay? So it's a crucial point that we allow this to happen slowly. Eventually, a catalyst will reduce and it will speed up. So this introduces then some subtleties. This object up here is a bona fide RAF. So I start with this reaction that has two food molecules, produces this product, and then this produces this. And you see the catalyst for this reaction, up here. Yeah, this product catalyzes this reaction, that's right. And we got there. Now this down here, you notice that in this one up the top, this reaction has to happen first, but its catalyst is only produced once we've gone all the way around the cycle. The single catalyst for that first reaction is P4. So that's an example of what I just said in that last slide, that those reaction goes slowly until P4 is produced, and then they speed up. This, on the other hand, is the stronger notion of what we call a CAF, constructively autocatalytic. So here, everything has to be catalyzed when it's needed. It's a much stronger notion than a RAF, but it's completely the wrong notion, as we'll see shortly. And this system over here looks like a RAF because every reaction is catalyzed and we've got the food source around the outside. So why is it not a RAF? Well, what reaction would go first? The first reaction can only have elements of the food set as its input. Can't be F1 because F1, it can't be this reaction because it requires P3, and can't be this one, it can't be that one. So this system, once it's going, it can keep going, but it can't get going. It can't form. Okay, so we call it a pseudo-RAF. These distinctions really only become apparent when you formalize these notions mathematically. They tend to be glossed over if you just wave your hands and talk about autocatalytic sets. So there's some benefit in sort of sitting down and carefully writing out what is the definition, what you mean. So back to Lifson's criticism of Kaufman. Let's let mu be the average number of reactions that each molecule type catalyzes. So under Kaufman's model, it seemed that you needed mu to grow exponentially with n. So I was interested in how fast does it really need to grow with n in order to get a RAF forming. If it is less than a constant, the probability your system of polymers has a RAF goes to 0. That constant was quite small. And if it's quadratic with n, the probability that there's a RAF within your system goes to 1, becomes certain. On the other hand, if you're interested in a CAF where everything has to be catalyzed the first time it's required, you need mu to grow exponentially with n. So there's, although those distinctions I showed you in that last slide seem quite subtle, they have enormous implications because here we have quadratic, here we have exponential. Yeah.
How is the probability distribution defined?
Sure. So good question. This Pn, it's the probability that my catalytic reaction system contains a RAF. So what's random here? What's random is the pattern of catalysis. The actual set of reactions is just all the cleavage and ligation reactions. So that's deterministic. The only randomness comes about by virtue of the catalysis. And the catalysis is random, as you assume that each molecule catalyzes each reaction with a given probability. This is the simplest model.
So it's some kind of independence assumption.
Yes, strong independence assumption, uniform. Yep, good question. So what else can we show? We can show that if a system has a RAF, it has a unique largest one, which we call the max RAF, which is a nice mathematical result. And we also, you can imagine a system with thousands or even millions of reactions and molecules, and you want to know, does it contain a RAF? You don't want to search all of the possible subsets, but there is actually a fast algorithm, and we use that a lot in our subsequent papers, that takes any catalytic reaction system and calculates the max RAF. If there is no max RAF, it just says there's no RAF in the system. Let's say, I think it's an order n squared log n, maybe n cubed algorithm. Okay, so this is what we learned back in 2000, but the person that reviewed that paper, who later identified himself as David Sankoff, said, he said, I really wanted you to conjecture what the right value of dependence on n would be for RAFs to appear. So I just said, in the paper, I said, I conjecture it's subquadratic. I had no idea. But I had this guy, Wim Hordijk, who's a professional postdoc, travels the world. He's got a lovely webpage, Wim's Worldwide Wanderings. And he came into the one-year postdoc with me, and it was great. And I told him about this problem. He said, oh, that's perfect. I've just been at Santa Fe working with Stu Kaufman. I love autocatalytic networks and stuff. He said, let's do some simulations. I said, Wim, we are a maths department. We do not do simulations. We have to prove a theorem. Anyway, Wim did some simulations, and boy, was that useful, because here's what he found. This is the amount of catalysis you need. So this is how many reactions on average will each molecule catalyze, and this is the n, and this is for the probability of a RAF being 0.5. And look at this. What does that suggest? It says mu is going to be linear with n, which and what's also striking about this is, although Kaufman's argument said mu had to grow exponentially with n, look at this, like, sequences of length 12. You just need each molecule type to catalyze on average 1 or maybe 2 reactions, which is not a lot. It's certainly in line with the type of catalysis rates you might find in primitive biochemistry. Anyway, it took a while to actually do the mathematics. This wasn't with Wim, it was Zelkana and Marcel, but we were able to show that indeed it is linear. If you are less than linear, the probability of there being a RAF goes to 0. If you're as fast as linear, it goes to 1. In fact, we proved something more strong, that it really grows exactly linearly with n. Whereas the emergence of a CAF requires, that's that stronger notion, requires mu to grow exponentially with n. Okay, so let's go back to Kaufman. Kaufman liked to keep P fixed and let n grow. So let's let P be, each molecule has a probability of 1 in a million of catalyzing any given reaction. As we're increasing n, of course, the number of molecule types and the number of reactions is growing exponentially. And this is the probability your system contains a RAF. So, 0 up to 15, and you add one more allowed polymers of length 16, and it goes up to close to 1. It's a very sudden transition, the appearance of RAFs, as you just allow your sequences to have maximum length up to 15. You allow one more, and suddenly it's gone up to close to 1. It's so what can we say mathematically about RAFs? We can say quite a bit. I'm just going to restrict to the binary polymer models with uniform catalysis. So when RAFs first appear, it turns out that they are big. They're not as big as Kaufman's ones, which would have been all of the reactions. In fact, the proportion of reactions that are in the max RAF when they first appear is quite small, but they involve most of the molecule types. So this is the, here is the expected number of reactions each molecule catalyzes. And when a RAF first appears in these simulations of bins here, they had about 1,400 reactions, but inside them, there are these smaller RAFs. So this is the size of that max RAF. Remember, every system that has a RAF is always contained in this max RAF, but sitting inside the max RAF can be smaller ones. And you can look at the smallest ones. These are called irreducible RAFs. But we can prove that, see, these are still of length 600. You might think, oh, maybe there's a small RAF in there of size 10 or something. And it turns out that you can prove there is no, at this low catalysis rate, where RAFs are starting to form, there are no small RAFs. And that's interesting because, you know, going back to that first slide where we had cycles forming in random digraphs, when cycles first form, there are small cycles and big cycles. There's cycles of all lengths. Most of them are quite small. Whereas here, we don't have that. And the reason, I think, is because we're coupling together these two properties. Not only must there be a cycle in some sense of catalysis, but also the system must be food set generated. So I think the combination of those two factors is the reason for that. On the other hand, if you move away from the simple model, each molecule catalyzes on average the same number of reactions, but it could be that, and this is closer to real biochemistry, it could be a small number of molecules catalyzes a lot, and other molecules catalyze far fewer. So we looked at models that were heterogeneous in their catalysis rate, and we were able to show that you can get quadratic size RAFs arising. Now, this is a collection of reactions that forms a RAF. This was actually randomly generated in BIM's binary polymer model simulator. So this is this description of this catalytic reaction system. And this has a number of RAFs sitting in it. So R3 by itself is a RAF. The food set here are just the monomers, 0 and 1. R3 is a RAF because, monomers and dimers, I should say. So 1, 0, 1, 0, and 1 are both in, this is the food set here. They are both in there and it's catalyzed by 0. So, okay, R3 is a RAF. But there's all these other RAFs here. And you notice these arrows pointing up denote containment. So this is what's called the Hasse diagram of this partially ordered set of sub-RAFs. This is the max RAF up here. Why is it red and why is that red? Well, because these are closed RAFs. I won't go into that detail. But what are the smallest RAFs in the system? The irreducible RAFs. They are the ones that don't contain any other RAF. That would be this one and this one. So there's 2 irreducible RAFs or minimal RAFs in that system. Okay, so that's all the sort of theory in simulations and so forth. So I want to turn now to some experimental studies. One of the first I want to discuss is this paper appeared in Nature by this group in Portland, where they were able to construct a small-scale system of RNA ribozymes that were autocatalytic in some sense. And this was the corresponding catalytic reaction system. It's a little bit hard to see what's going on here, but what I've done up here is I've drawn these reactions, these 7 reactions, and I put an arrow from one reaction to the other if the first one has a product that catalyzes the second one. And so then we can look at that directed graph and consider it strongly connected components. And we were able to extend some of the work in that paper. They identified that this was a RAF, but we were able to actually find lots and lots, 67 RAFs, in fact, are present in that system. And this is the Hasse diagram of the relationship between all of those RAFs. The idea of the Hasse diagram is, well, that's what we, maybe this, you have some system you see today, but how did we get there from something more primitive? We did another study as well of an early paper by, this was a peptide autocatalytic system produced in the 2004 by Ashkenazi. And we found in that system 305 RAFs, 6 min RAFs. But perhaps more interestingly, we started looking at real biochemistry. So in work with Felipe Sousa and Bill Martin, this is a few years ago now, we wanted to take some sort of primitive organism and look at its, think of its metabolism as a catalytic reaction system and say, well, what RAFs are in there? Now, so this is the tree of life, of course. So we've got bacteria here, and we've got the, sorry, this is the archaea, the central lineage. I'm going to talk about that shortly. Archaea are possibly the best contenders for early life, but bacteria are also pretty primitive compared to us. So we thought we wanted to take something really primitive, but not much is known about biochemistry of very primitive bacteria. So we decided to go for E. coli, which is extremely complicated, but so well studied that there's a detailed knowledge of the biochemistry and metabolic network for E. coli. And so we were able to analyze that using a food source of 438. We found the presence of RAF, a large RAF set, but not a CAF. And we were able to analyze the sub-RAF structure. We were able to do some things like say, well, how much of the food set could we throw away and still have a RAF present? So although there was that much food set, we could get it down to 123 molecule types and still have a RAF present. We also looked at what happens if you start knocking out reactions in the system. It's typically what happens is not much happens for a while, and then suddenly there's a drop, and then there's about 2 or 3 drops till you get to 0. They're quite sudden drops. More recently, this is work with Joanna Xavier, who's a extremely productive worker in this area. And this was also with Bill Martin and Stuart Kaufman. We looked at, we wanted to take more primitive organisms than E. coli. So we took a methanogen, I think it was. So that's in the archaeal lineage, and an acetogen. 2 very primitive organisms. One of these organisms lives in these hydrothermal vent type conditions, and we analysed the RAF structures, both of those 2, to see what they had in common. We also looked actually at the intersection of the max RAFs of those 2. So this is the max RAF of the metabolic network of the acetogens with the max RAF of the methanogens. And from this, it was possible to, I mean, it's still a very large complex, but it was possible to identify what are the main molecule types here that are really essential. Things like, if you remove that, suddenly there's no more RAF there anymore, or it collapses significantly. That's quite a long story. I don't want to go down the details of that too much, but I will mention that just this recently, this is in this year, Joanna has spent, again, a huge amount of work. They've analysed 6,683 prokaryote metabolic networks and determined the maximum RAF size of those across all of those, and looked at what they have in common. The goal here is to see, if you look across all these, primitive forms of life, that exist today, what are the common features? How might you explain how they got to where they are from something more primitive, perhaps? That's the goal. Just two last things on RAFs. Sometimes people say, well, yeah, okay, catalysis is all fine, but sometimes molecule types inhibit reactions as well. So it's easy to handle. Instead of just having catalysis arcs, you allow inhibition arcs, these red arcs. So that means that if Z is present, then that reaction R1 prime can't take place. Okay, so then you can talk about the notion of an uninhibited RAF. So it has to be a RAF, but no reaction in it should be inhibited by a product of another reaction. So in this example here, that whole system there is not a RAF, even if I ignore the red stuff. But R1, R2, R1 primed, and R2 primed are RAFs. That set of 4 reactions is a RAF, but it's not an uninhibited RAF. I can't have all 4 of those because why is that? Well, because the product of this one inhibits the first one. Yep.
Is this a case where having inhibition actually makes it into a RAF?
I don't think so. I don't think that could happen, but or you mean into an uninhibited RAF, or yeah, it could actually. I see where you're coming from, but it would have to be a RAF to begin with. Ignoring, yeah, good. Yeah, so there's a simple heuristic for searching for a URAF, which is simply just compute the max RAF, throw out all reactions that are inhibited, and then compute the max RAF of what remains. Now, you might get the empty set, in which case, well, you don't know whether there was a URAF there or not. But if you don't, you get a URAF, which is kind of nice. It turns out, unfortunately, though, that the problem of determining whether a system has a URAF or not in general is NP hard. So there's no good algorithm like there is for RAFs. Okay, final slide on RAFs, I think, is that they've been applied in other settings as well. So Wim Hoerdijk and his colleagues have done some applications in ecology. Stu Kaufman likes to talk about the economy as some sort of a RAF, you know, like when you build a table, you take wood and your nails and you hammer the wood together. So you're using the wood and the nails to make a table. The hammer is the catalyst because it's not used up in the reaction. It's just the thing that makes it happen. But that hammer in turn is the product of some other reaction. And, you know, a factory would be like a catalyst as well. So, you know, you can think of the economy in some sense as a RAF. Some things are used up to make others, and some things facilitate that process without actually being used up. I have been working with a cognitive psychologist in Canada, Leanne Gabora, on cognitive modeling, in which particularly, I think we have about 4 or 5 papers on this. This first one was on the transition from episodic to mimetic cognition. So the idea, I'm not going to have time to talk about this. The idea is just basically we have long-term memory, working memory, and stimuli. And at a certain point, you get the possibility that items in working memory can catalyze other ideas, and you get these formations of what we called cognitive catalytic processes taking place, which at a certain threshold take over, and you get the formation of a new type of thinking. Anyway, that's a long story, and I won't go into bore you with the details of that. Okay, sorry, just going to flip them. Yes, so this is unrelated to RAFs. It's something, though, that Stu Kaufman got me interested in. It's this idea that a lot of what is invented is the result of somebody taking 2 or more ideas and putting them together. So in fact, yeah, this paper here makes that clear, that a lot of inventions combine at least 2 previous technologies. So one way to model this was Roger Copel. If you let nt be the number of items at time t, so at the next time step, you've got the ones that were there already, and then you've got, you could have take the number of ways of taking 2 things. This is nt choose 2, and then you weight that by a certain small number. and then you'd have the number of ways of taking three things and combining them, weight that by a small number. So he came up with this formula called this is Kaufman's, it's the adjacent possible, which and if you draw a graph of this, it looks kind of strange. It doesn't look like, it's not linear, it's not parabola, it's not exponential. It looks like this, sort of a hockey stick shape. And it's kind of looks like there's going to be a vertical asymptote here. It's going to go to infinity in finite time. And some claims were made about that at the time. But if you look at that equation, you see that it can never be infinite. Why? Well, time's discrete, and it's proof by induction. If mt is finite, then mt plus 1 is finite. QED, I mean, it can't be infinite. There's never a time when it's going to be infinite. What is this graph on the right? That's world GDP. And you might think, well, maybe that supports the idea, inventions, a lot more inventions now. But then you think, oh, hang on a minute, there's way more people alive today than there were in the past. So let's take world GDP and divide it by population. Oh, well, it doesn't make a hell of a lot of difference. Okay, so I got interested in this because, first of all, I didn't like this discrete feature of it. And I didn't like the fact that it was deterministic. I hate deterministic, I like stochastic. So I thought, well, let's replace this by random variables and do it in continuous time. And we'll also allow extinction as well. So mt plus delta, it could go up by 1 or down by 1 if there's an extinction event, linear extinction. And the plus 1, this reflects the term in the Koppel equation, but it's done carefully now so that this mt is always an integer. Yeah, we get the same behavior. Now, what happens to this process? Does it reach infinity in finite time? Not necessarily. It could go extinct. It could just go down to 0. It's not guaranteed, but we can prove something. We have to make a mild assumption that, you know, there's the possibility of combining at least two things, and also alpha I is not 0 for some I less than m0. So yeah, you can prove this theorem. It's probability 1, it explodes or becomes extinct. And the interesting thing about this is that the expected time till that happens is finite. So in finite time, it's guaranteed to either go extinct or explode. Just recently, Stu and Wim were interested in combining these two ideas, RAFs and the adjacent possible, is what I've just been talking about. And in a way, some of these ideas go back to Enquist and colleagues where they're doing modeling cultural evolution, because they had notions of sort of catalysis and combining different ideas to produce new ideas. But we just formalized that a little bit more. So we allowed now not only the catalysis to be random, but the network to be generated by that adjacent possible process where, you know, three things could combine to produce something new, all done randomly. And in that case, you can show exactly what the catalysis rate you need for this system to be a RAF is. Okay, that's part 2. Part 3 is quite short, so I hope to finish in 10 minutes, so allow time for questions. So this is my bread and butter business, is phylogenetics. Yeah, so evolution's happened, all species trace back to what we were talking about at the start of the talk, origin of life. And we happen to come along at the present and look across the tree and say, right, that's what we see. We don't see these lineages that have gone extinct. We just see what's called the reduced or reconstructed tree. And what does that tree tell us? Well, just if we ignore the names of the species, who cares what the species are? Let's just look at the distribution of little branch lengths. So these have long interior branches and very, very short pendant branches. Those branches near the tips This is the sort of tree that you get in population genetics with the Kingman coalescent, which is well known to some of you. On the other hand, this tree, the branch lengths are all pretty much the same as you go up and down the tree. So branch lengths is one aspect of tree shape. The other is balance. So this tree, as I go up the tree, I look at how many are on the left, how many are on the right. You know, it's roughly 50-50, but here it's dramatically different. It's a very unbalanced tree. At each point, there's way more on one side than on the other. Okay, so that's another aspect. That's a discrete statistic, whereas this is a continuous one. And they are really the two measures of tree shape that are important in phylogenetics. So what should we expect to happen? George Houdini Yule, way back in 1920 or around there, maybe even earlier, he modeled how a single species could form into a tree. You'd have a constant rate at which each lineage splits and a constant rate mu at which each lineage would go extinct. So as most people who've done probability will know, if the rate of speciation is less or equal to extinction, this tree is guaranteed to die out eventually. On the other hand, if the speciation rate is bigger than extinction, then it'll either die out or the number of tips will go to infinity as time becomes large. So we're going to assume that latter scenario from now on, and we'll let NT be the number of species alive at time t. This has a geometric distribution with, as you might expect, e to the lambda minus mu t. Okay, so what can we say about the edge lengths of the reduced tree? If I just take a randomly selected edge from the reduced tree, it's roughly 1 over lambda, or might be 1 over 2 lambda. It's a little bit complicated because it depends on mu and lambda, but it's sort of like constant over lambda. But recently we got interested in, well, what's the length of the longest edge that is still alive today on the tree? And we get this quite remarkable result that for the reduced tree, if I divide by the total lengths of the tree, converges in probability to a half. And why that's surprising is it doesn't mention lambda or mu at all, just somehow it's a half. So we proved the theorem and thought, oh, well, we should perhaps look at some real trees and see if that's true or not. And well, here's a tree, a typical tree where, yeah, you see about half the length of the trees these are various mammals. Half of it's taken up by that species there. So we actually looked across a large number, 114 mammal families. And as the trees got bigger, you see this tendency towards this 0.5 relationship. So it's a sort of an interesting prediction that we're quite pleased the biology didn't contradict it. Another application of these ideas is it's very topical at the moment, given the mass extinction event we're in, is trying to predict how much biodiversity would be lost if, you know, a certain percentage of species were to go extinct in the next 50 years, or whatever. So this is the tree of all 10,000 species of birds that was published quite recently, and yeah, so I think there's about 575 bird species that are on the imperial, you know, on the danger list for the IUCN, and if it's estimated that if all those were to go extinct, you would lose a combined total of about 2.7 billion years of evolution if you include the lengths of all of those branches. Of course, some of them evolving together, so you're double counting to some extent. So, but why the study of edge lengths is important is one of the reasons we got interested in it was this much cited paper by Sean May and Lord Robert May, that 80% of the underlying tree of life can survive even when 90% of the species are lost, which is kind of quite a provocative statement and not very good for conservation purposes. The reason they found this is they were using these trees over here that have these very, very short pendant branches. And when you do this on a birth-death tree, this is what you get, for example, with pure births. This is the proportion of the tree surviving. What's this S? S is the proportion of species surviving. So when you do that, you find that actually the loss of 95% of species would lead to only 16 to 20% of the tree surviving. So it really makes a big difference which model you use. Your conclusions will be completely opposite almost. Okay, tree balance. As I said, some trees are very unbalanced, others are not. David Eldis did a very insightful study early on where he looked at, he went down the tree and said, you know, what proportions on the left and the right, and he fitted this beta model to it. And this beta equals 0 Markov model, that is the birth-death process prediction. But he found that this beta equals -1 fitted this data much better. This is a beta statistic for his analysis. And it's been a real, I guess, something that mathematicians, probability theorists, even biologists have really aimed to try and understand is, can we explain why trees are less balanced than they should be as predicted by the birth-death process? So Eldis said he didn't know of a natural candidate for it. Amuri Lambert and Tanya Stadler have made some important advances in this problem. They said, well, maybe speciation rate depends on, maybe it depends on time, maybe there's rapid bursts of speciation, and maybe it depends also on how many species are there. If there's a lot of species, maybe it's too crowded for new species to form. Same with extinction, it might depend on time. You might have the Cambrian explosion, sudden loss, maybe it depends on how many species are there. Maybe it depends on the age of the species. What's the age of the species? The age of that species there is how long back the last speciation event. Maybe a species that just formed has a much higher extinction risk because it's new, hasn't learned to survive. So could this explain why trees are not as balanced as birth-death models predict? No, unfortunately not. All these models lead to exactly the same beta statistic. So is there hope? Well, actually there is a little. If you allow, you see there's a slight asymmetry here. I've been cheeky and left out A in the speciation rate there. I put it there, but not allowed it there. Even if you just allow lambda to depend on the age of the species, and even if you take mu to be constant, you can get trees that are as unbalanced as we observed, that beta equals -1. Okay, so that's me. Hope you enjoyed the talk and happy to answer any questions. Yeah.
In the first part of your talk about the routes, as I understood it, all of the models that you talked about were based on this sort of polymerization, sort of ligation reactions and cleaving reactions.
In that very first part, but in the general framework, we don't make any assumption at all about what the molecule types are. So most of that RAF theory is generic. So it's divorced from but some of the specific results, like how much catalysis you need, that did depend on the polymer model, for example.
But whenever you're generating the network, you have to have some process for generating the topology and then for statistically assigning probabilities to reactions occurring, right? So in general, when you're doing that, you're using the polymerization and ligation reactions. Is that?
No, no. We just assume that there are, there's this probability given to us by somebody. Yeah.
Okay. Yeah. Thank you.
Okay.
Sorry.
The question about the second part, combinatorial growth. I had a look at this paper early on. We related it mostly to the growth history and industrial revolution. I don't remember that we related it to the theory of adjacent possible. Maybe at a later point they did. I'm just curious how do we come together combinatorial expansion?
Yeah, I mean, I never used the phrase adjacent possible. I just mentioned it because Stu used it. I mean, we had a bit of but yeah. Yeah, I mean, he often talks about how, you know, all the uses of a screwdriver and how, yeah. So I just took a more kind of abstract approach of, you know, you combine two things or three things, and
Basically, you see that as a way to reach out into this adjacent possible by exploring combinatorial permutations.
Yeah. Yeah. Peter.
Michael, just wondering if you can get over Liston's objection by just looking at the reactions that join two ends and defining the ends, because then if you go out from the ends, you automatically get your two to the N or whatever this molecule have those ends on it. If you do that systematically, can you just give him a negative answer?
Yeah, I guess I was just working on, you know, he criticized the original Kaufman model, and I was just working on that, and I didn't try to modify it but I just was interested in whether, you know, you could still find a subset that was, you know, if you still needed exponential.
Yeah, but that what I was saying would be more realistic, because otherwise you end up with the idea of Kaufman model, you end up with the idea that you can have two enormously long molecules, and then you have this little short molecule which recognizes them specifically, those long ones, somehow joins them together and doesn't do anything else. That's what you get when you put random intelligence.
Yeah, no, I haven't looked at that. I mean, that could be a good thing to look at, but yeah, I guess our focus has been more on looking at these real networks now rather than the polymer ones. Yeah. Alan.
Just about the $3 slide, is that the one before?
Yep.
Is A get smaller? Does $3 get more retreated than $1 or
Yeah, if you have a model in which when a species forms, it either splits again quickly, or you know, if it goes too long, it doesn't. So that would, I guess, be the rate would be inversely proportional to A. In that case, you get unbalanced. Yeah.